Welcome. In today's video, we're going to be talking about understanding congruence in terms of rigid transformations. The Common Core standard that this aligns with is High School Geometry, CO.B.6, and the standard is to use geometric descriptions of rigid motions to transform figures and to predict the effect of a given rigid motion on a given figure. Given two figures, use the definition of congruence in terms of rigid motions to decide if they are congruent. Let's get started. So we have three goals for today. First, we're going to learn about some rigid transformations. Next, we're going to learn about composition of transformations. And third, we're going to discuss a little bit on triangle congruence. So here are some keywords that we need to know for this. So first, we need to know that a transformation is an operation that moves, flips, or changes a figure to create a new figure. A rigid transformation is a transformation that preserves size and shape. And a non-rigid transformation is a transformation that does not preserve size. Some other things. A pre-image is the original figure before a transformation, and an image is the figure after the transformation. And one more thing is a vector. A vector is a quantity that has direction and size. So what exactly are rigid transformations? We're going to talk about three rigid transformations. We're going to talk about reflections, rotations, and translations. So a translation that does not change the size or shape of a figure is a rigid transformation. Here we can see a reflection depicted with a triangle. So here we have our pre-image, which is what the object looks like before the reflection, and here we have our image, which is what our triangle looks like after our reflection. And here we see the same things depicted with a rotation and a translation. So reflections are an image or a shape as it would be seen in a mirror. So let's say you had a mirror right here along the x-axis. The reflection of A is triangle B. What's great about reflections is that when you reflect a figure, it remains congruent. The shape is exactly the same. Here's some more information about reflection, namely over the y-axis, the x-axis, the line y equals x, and the line y equals negative x. Now let's talk about rotations. So a rotation is a circular movement. It has a central point that stays fixed and everything else moves around that point in a circle. And rotations are a full rotation when they're 360 degrees. So that's a full circle. Here we can see our triangle A and the image B, which is this triangle rotated. Here's some information about what happens to the coordinates when you rotate by 90 degrees, 180 degrees, and 270 degrees. Here's the same information presented in a different form. Now let's talk about translations. Translations are when you slide or move a shape without rotating it or flipping it. And the shape looks exactly the same, it's just in a different place. So here we had our shape A, and we went ahead and translated it to B. And again, the objects A and B are exactly the same. They're still congruent. So what is one thing reflections, rotations, and translations have in common? They are all rigid transformations, so objects that undergo these transformations remain congruent. This is what you can do on your own. Try to identify the type of transformation you see in each of these four pictures here. Now let's talk about composition of transformations. When transformations are combined, the resulting transformation is a composition of transformations. So here we can see we have our blue triangle, and first it is reflected over the y-axis, and then it is reflected over the x-axis. So this is a composition of transformations because it is more than one transformation. And here you can see that any composition of transformations can be simplified and written in a different way. So on this side, we see the blue triangle go directly to the green triangle, and it's by rotation of 180 degrees. So more about compositions. So a composition of two or more isometries is an isometry. Each isometry is a rigid transformation. So after performing several isometries, the figure does not change the shape or size of a figure. We can think of the series of isometries as a single isometry. So that's what I was talking about before. You see here that we have our image here, and we perform two transformations to it, but there is one single transformation that takes the pre-image to the image. Let's talk about glide reflections now. A glide reflection consists of a reflection and a translation in a direction parallel to the line of reflection. It doesn't matter whether the reflection or the translation is done first. The composition can be written as a single rule. So in this picture on the left, we see that the reflection of the blue pentagon over the line, and then we see the red pentagon translated to become the green pentagon. And in the image on the right, we see the blue pentagon translated first and then reflected. But you can see that no matter which order you did it in, reflection and then translation, or translation and then reflection, the blue and green objects are in the exact same place. That means the pre-image and the image are the same, no matter what order you perform these two transformations in. Now let's talk about reflection over parallel lines. So here we can see that we have a composition of reflections over parallel lines, and it's equivalent to a translation. So reflections over parallel lines theorem says that if there are two reflections over parallel lines that are h units apart, it's the same as a single translation of 2h units. So let's look at these two pictures. So let's look at this image down here first. We have our pre-image of triangle ABC, and it's going to be reflected over that parallel line, and then it's going to be reflected again over the second parallel line. And when you do that, you have a single transformation of 16 units, as in this example. Next, we have reflection over the axes. Reflection over the axes theorem says that if there are two reflections over each axis, then the final image is a rotation of 180 degrees of the original. So we started off, and lastly, we have reflections over intersecting lines. So two reflections across two intersecting lines is equivalent to a rotation. So the theorem says that if there are two reflections over lines that intersect at x degrees, then the resulting image is a rotation of 2x degrees, where the point of intersection is the center of rotation. Another theorem says that any translation or rotation is equivalent to a composition of two reflections. So can we use rigid transformations to show that two figures are congruent? Well, yes, because rigid transformations preserve angles and sides. So now we're going to talk about triangle congruence. So how exactly do you prove that two triangles are congruent? Well, I'm going to show you about 4 methods you can do that today. Before we get into that, we need to talk about congruence statements. So here we see two triangles on the left side. We see the triangle ABC and triangle DEF. So I created these two triangles. I just copied and pasted one another so I know that they are congruent. So now I have to write some congruence statements. So first I know that triangle ABC is congruent to triangle DEF. And now I need to tell you about the congruence of the sides of the triangles and of the individual angles. So I have to see which parts on the triangles correspond to each other. So I see here that I have angle A right here. And if I'm going to look over to this triangle directly over, I see it corresponds to angle D. So I know that angle A has to be congruent to angle D, which is the first congruent statement I had right here. And if I'm looking at the way I wrote my triangles in the first place, I said ABC is congruent to triangle DEF. So I'm going to look and see, oh, well, angle A, that's the first placeholder in the way I wrote this triangle, and that's congruent to angle D. So I did those for all 3 of the angles of the triangles, and then I have to compare our segments. So I'm going to look again and say, oh, here I have segment AB, and that is congruent to segment DE. So that's my statement right here. I have segment AB is congruent to segment DE. Now if I'm going to look at this bold statement again, I have A and B, which is the first 2 letters of this, and then I have D and E, which is also the first 2 letters of this triangle notation. So that's one way that we can write our congruence statements. And for any given pair of triangles, you're going to have 6 congruent statements, 3 for the angles and 3 for the segments. So here's an example of triangles, and they are congruent. Now you have to write your own 6 congruent statements, and once you're done, discuss that with a partner. So now let's talk about the ways that you can prove that 2 triangles are congruent. Well, first, we have the side, side, side theorem. So this theorem states that if all three sides of a triangle are congruent to all three sides of another triangle, then the two triangles are congruent to each other. So in this picture, we can see that the side XZ is congruent to the side AC because it has one tick mark. Then we see that side BC is congruent to side YZ. So they have two tick marks on them. And then we see side AB is congruent to side XY, and they have 3 marks. So since all the sides in triangle ABC are congruent to all the sides in triangle XYZ, we can say that these two triangles are congruent because of the SSS theorem. Next, we have the angle side angle theorem. So this says if you have an angle, a side, and an angle congruent in 2 different triangles, then the 2 triangles are congruent. Now about this theorem, we have to make sure that our angle and our side and our next angle are in this pattern. So the side has to be in between the 2 angles in order for this theorem to work. So we see here that angle A is congruent to angle X, angle B is congruent to angle Y, and side AB is congruent to XY. So therefore, we can say that these 2 triangles are congruent by the ASA theorem. Next, we have our side angle side theorem. So this one is kind of similar to the last one in that we need to have something in between the other 2 things. So here we can see that we need a side and an angle in between the 2 sides and another side that are congruent. So we see here that this side is congruent to this side because they each have 1 tick mark, and this side is congruent to this side as shown by the 2 tick marks, and then we have these 2 angles congruent to each other. So we can say that these 2 triangles are congruent because of the SAS theorem. And the last one we're going to talk about today is the hypotenuse leg theorem. So this is specifically for right triangles. If you have 2 right triangles, we can say that they are congruent if the hypotenuse is congruent to the other hypotenuse of the other triangle, and the leg is congruent to the other leg of a triangle. And so if you have the hypotenuse and a leg of 2 right triangles congruent to each other, then you can say that the 2 triangles are congruent because of the hypotenuse leg theorem. One important thing to note is that we should avoid donkeys in math class when proving triangles are congruent. So we do not want to see side-side angle, and we do not want to see angle side-side. You cannot prove that 2 triangles are congruent by using those 2 things. It just won't work. So don't do it. So in class today, we had a handout that we were able to use an applet called GeoGebra, which we've used in class before, to show triangle transformations and then to show that the triangles are congruent once we do the transformations. So on the website, you can access the handout that we saw today, and you can follow the instructions for using GeoGebra to create your own GeoGebra triangle transformation construction and then prove that the triangles are congruent. So we went over that, and also in class, we did a few questions of classwork, which just tested more GeoGebra constructions and also had a few questions that you had to explain about triangle congruence and transformations. So your homework for today is to go to this website, student.desmos.com, enter in the class code FD576E, and complete the activity. This exit ticket, which I would like you to bring in when you come back to school, I would like you to answer these 3 questions on a piece of graph paper and then hand it in when you come back to school. So these questions say, which of the theorems we discussed in class would you use to prove that the triangles are congruent? You do not need to write a formal proof. We did not go over how to write a formal proof in this class, so I just wanted you to say if you would use side, 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 angle, side, angle, side, or HL, any of the 4 that we discussed today. The next question is to reflect triangle ABC over the line y equals 3, and then reflect that image over the line y equals -5. And lastly, we have find the translation rule for the triangle TRI to its T prime R prime I prime triangle. So be sure to do this and bring it in with you to class tomorrow. So this is what I hope to accomplish in our continuation of this unit. So I want you guys to be able to independently tell me sequence of rigid motions, composite and function notation, which we didn't get to talk about a lot, I need you to be able to write the sequence of corresponding sides and corresponding angles, and then give me a congruent statement at the end of it. So hopefully after a few more classes, you guys will be comfortable with this and will be able to do that on your own. So thanks for watching, and I hope you learned a lot about this.